Hello, everyone. Welcome to Pre-Lecture 16. This will be looking at acids and bases again and starting us with some calculations as well. Okay. This was a slide from last class where we talked about essentially how to interconvert between pH, POH, as well as our concentration of hydronium in solution and our concentration of hydroxide. One thing that I had forgotten to point out in class and just wanted to make sure that you saw was we look at towards the bottom here, if we're interconverting between our concentration of hydroxide and hydronium, wanted to give you the value for Kw. And so Kw, of course, is our equilibrium constant for water, the autoionization of water. And so that value is 1.0 times 10 to the minus 14. And then, of course, pKw is then pH plus POH, which is then equal to 14, of course. Okay. Right, so that was just something that I had forgot to bring up last class that I wanted to make sure you knew about. If we go on, we can also then discuss the difference between strong, weak, concentrated, and dilute acids and bases. And so just a reminder that anything that is a strong acid or base will completely dissociate when it is dissolved in water. Another way to say that is that it totally ionizes. And so this is the definitive list of strong acids and strong bases that you need to know. I'm generally not a person who encourages memorization for chemistry exams, but these are things that you may just need to memorize. And so these are our strong acids shown here: HCl, HBr, HI, HNO3, which is nitric acid, HClO4, which is perchloric acid, and sulfuric acid, H2SO4. For all of our strong acids, they're going to be our metal hydroxides from the first and second column of the periodic table. So lithium, sodium, potassium, calcium, strontium, and barium hydroxide. Okay. Right, and then, so those are what make up our strong acids. I'll also remind you that our weak acids and bases will only partially ionize in water. And so, for example, here we have the acid ionization constant, equilibrium constant, which is just our products over our reactants, of course. And for all of those reactions, our reactants will be generally what is favored. Okay. So those are strong and weak. If we then talk about concentrated versus dilute, when something is a concentrated acid or base, typically we mean that it has a concentration that is greater than 1 molar. And so even if you have a weak acid, if it is very concentrated, then it can still be very dangerous. Okay? So just because an acid is weak does not mean it is not dangerous. Similarly, a strong acid can be then dilute, and it can be relatively non-harmful. And so if our strong acid is dilute enough, say in the range of 10 to the negative 6th, 10 to the negative 7th for a concentration of hydronium ions, then that is essentially no longer harmful to us. And so it's close enough to neutral that we wouldn't call it a harmful acid if it is diluted enough. Okay. Right, so to again just kind of give you a scale here of different acids and bases, their relative strengths. Our strongest acids are shown up top here, and then we get into weaker and weaker acids as we go down the left column here. So water, of course, being our neutral atom, but we can also have weak acids like hydrogen carbonate, hydrogen cyanide, ammonium. Those are all weak acids as well. Then we have things that do not undergo ionization, but can also be present. Then, of course, when we get to bases, you can notice that our weakest bases are the things that are our strongest acids. And so we'll talk a little bit more in class about how these conjugate pairs tend to make basically the stronger the acid, the weaker the conjugate base. the weaker the acid, the stronger the conjugate base. If we're thinking about it like that, and of course, vice versa. So if we were to look further down, maybe look at the hydroxide ion. The hydroxide ion, of course, is very basic. So because our base is very strong, our conjugate acid, being water, would be very weak. So those strengths tend to be basically inversely related. And so I want to take some time to finish up this video talking a little bit more about Ka and Kb. And so we've already said that our weak acids will only partially ionize in water. The same will be true for base. And so typically with bases, when we're writing our ionization, we need to include water. Again, as long as we're using our Bronsted-Lowry definition of acids and bases, we're going to need to transfer a proton from somewhere, and oftentimes that will be from water. Okay? So we have some sort of base, it reacts with water, we form a charged base species and a hydroxide ion. Then, of course, as always, our products over our reactants. So these are just our products over our reactant that is dissolved. Then we would leave water out, of course, because it is a pure liquid. And so as Ka or Kb gets larger, the strength of the acid or the base increases respectively. And so by the time we get around to something that is a strong acid, then Ka or Kb would be equal to approximately infinity, because at that point we have totally dissociated, and so we have entirely products, no reactants, meaning that we'd essentially be dividing by 0, which gets us to, again, basically infinity. Okay. And so just to put another scale to visualize this, we have stronger acids going from Kas of around 1, and then weaker acids all the way down to like something like water having 10 to the negative 14th for its acidic strength, right? Then, of course, the inverse then is true for our conjugate base. Okay. And so, of course, equilibrium is not going away. And so here's a practice problem for how you could determine K from data that was collected. And so let me get my drawer tool up here. We can go through this. And so this example, we're talking about acetic acid. Is essentially what makes vinegar vinegar, gives it its sour taste. And so the molecular formula is CH3CO2H, and we have a certain concentration of our acetic acid, and then we also have a certain concentration of our hydronium and our acetate, which would be our conjugate base. And this question asks us, what is the value for Ka? And so anytime you approach an equilibrium reaction, an acid-base reaction, I think it's always best to write out the chemical reaction that's going on as well as your equilibrium. And so we have our CH3CO2H that is dissolved, aqueous, reacting with water, which is our pure liquid in this case. That's going to be in equilibrium with our products, H3O+. So our hydronium will be dissolved, and our conjugate base, which will be acetate CH3CO2 minus. That will, of course, also be soluble. So we would designate it as aqueous. Then write our equilibrium expression. So Ka equal to our mantra, products over reactants. So concentration of hydronium multiplied by our concentration of acetate, CH3CO2 minus. Then all over our reactants. And so in this case, that would just be CH3CO2H. We, again, would not include water because it is a pure liquid. Okay? So that's our equilibrium expression. We plug in the quantities that were given as part of this question. We would end up with 0.00118 molar multiplied by 0.00118 molar, and then divided by our concentration of our reactant, which is this 0.0787 molar. Okay, and when we do that, do that math, I got that our value for Ka should be equal to 1.77 times 10 to the minus 5. Okay? So that would be how we calculate our acid dissociation constant, Ka, for acetic acid. Right? We'll continue to go through examples in class, but if you have any questions, please feel free to email me or let me know in class once we get there. Have a good day, everyone.